Yeah, you almost never see this. I, where possible, tend to shy away from using arrays of arrays simply because it can get quite confusing because of this property, the fact that we like to think of things as being nice and square and even, whereas in reality, I have no idea how, I have no way of telling how long each of these things are without looking it up. So I could say x.0.length, and it will give me, it will return 1. X.0.length of this one will give me 2, length of this one will give me 1, and length of this one will give me 4. So I have to look each of those up before I start doing anything on them, because just looking at one of these arrays is not enough. Likewise, if I said x.length, it would tell me how many of these there are, so there'd be 4. So I know that in the first thing there is 4 different arrays. Well, there's 4 int arrays, and then for each of those int arrays, for the first one there's 1, for the second one, or there's 1 int, for the second one there's 2 ints, third one there's 1 int, and the fourth one there are 4 ints. They get a little bit trickier as well with setting them up. So if we see down here, okay, so in this one they have set them up so that they're all the same width and height, but there's no, you don't have to do that. So the fact that they've said new float width by height, float width by height, is saying that it'll be more like that top case where it will always be width that way and height that way. But they don't have to do that. They could have set this up as more like the bottom example where, you know, for each one you basically say, I'm going to have 4 arrays of integers. In that first array of integers, I'm going to have 10 integers. In that second array of integers, I'm going to have 3 integers, and so on and so forth. It's not that uncommon to do things in 2D. Certainly, as I mentioned, in 3D, it's less common, but there are usually better data structures as well than just dealing with arrays of integers and arrays of floats where possible, because of these reasons it can get a little bit confusing to work with. Yeah. Does anyone have, does that make sense, kind of? It's a little bit of a confusing concept because, you know, we usually think of, what's it called, numbers? We usually think of, if we had a 2-dimensional array, we'd have something like what Excel gives us or like numbers gives us. Where we just end up with a big table like this and we can put values in it, but that's not necessarily the case. In this particular example, it is because they've said it's width by height, but it doesn't have to be. So yeah, it's good that this came up, but unfortunately it's one of those examples that you're like, kind of hope no one will find that or find something like that, because it is probably confuses things more than it needs to. But yeah, that is, when you see those double brackets or triple brackets or whatever, you're basically saying we have an array of something. So in this case, an array of arrays of integers. Yep, cool. Okay, otherwise, let's get back to our processing themes. So we talked about interaction on Tuesday. We talked about external libraries. I then realized that I probably should have told you guys what inheritance means in object-oriented programming, so we spent a little bit of time going over inheritance. Then we talked about user interfaces. We looked at Control P5 as one particular user interface. As I said, it is we're unfortunately sort of reaching that point now where in order to progress much further, we end up you know, with a bit of a step up in difficulty. That is not unique of processing, it's sort of the same in most languages. Unfortunately, Control P5 is one of the examples where it's probably needlessly complicated. I feel like perhaps if they'd had less flexibility in it, they could have made it a bit more, you know, this is how it has to work, and so design it that way, but they chose to increase the flexibility at the cost of having understandability, I guess, and that's a sort of common trade-off. But we had a look at a few examples. I showed you guys where to find more examples for Control P5, so hopefully if that's something you guys are interested in, There's lots of other stuff out there for you to look at. Otherwise, by the time we get to Unity, this will all seem like, you'll be like, why isn't it just this easy to do a user interface and everything? But it's always good to know what's happening behind the scenes as well. So we're going to move on to a few other, themes, and possibly we'll manage to get on to the next set of slides, which I think is graphics as well, which will be good because that is very applicable across all programming languages. But we're going to have a look at a few more things which are specific to processing. So first up, we're going to have a look at audio. So audio is, well, we all know what audio is, I probably don't need to explain it. But basically we're looking at sound as being a wave of air pressure. This is a bit of, I guess, a bit arbitrary for what we're doing. We don't need to know the physics behind it, but it will hopefully sort of explain what's going on in some of the examples. So we think of sound as a wave of air pressure. Effectively, we have some speaker or something, and that has a little membrane which moves back and forth, controlled by a magnet, and that will send out sound waves by compressing the air. And there's various things which control what we hear from the sound wave. So there is the volume, effectively, is how much this air is being pushed back and forth. So if it's pushing back and forth, it'll move our eardrums. So on the other side, I'll draw, that's what an ear looks like apparently. Inside that you have your eardrum, which has a little membrane which is connected to some bones and stuff, and then there's some hairs. And as these waves come into your ear, they push this drum, which in turn does some other stuff, I'm not a biologist, and then blows these little hairs inside your ear, and these hairs vibrate at certain frequencies and your nerves pick that up. So depending on the length of the hairs will determine what frequency they vibrate best at, and if I'm wrong on any of this, feel free to correct me. And then you detect that nerve impulse, and your brain interprets that as I've heard a sound at this frequency. So there's a couple of things which can determine how we hear things. So one is the volume, or how loud things are depends on how much this moves back and forth. So if it's moving just a tiny little bit, it's not very loud. If it's moving a huge amount, it's moving quite loud. And likewise, this is a speaker, but it could be my vocal cords vibrating the air and so on and so forth. And the other thing is the pitch, which is basically how compressed together these sound waves are. So if they're compressed really, really closely together, they tend to be quite high pitched. If they're spread quite far apart, they tend to be lower pitched. Okay, so we don't tend to illustrate things that way. We tend to illustrate things when we're talking about audio with waveforms. So if we have a graph for some time, if we drew a wave which looks like this, this is basically a sine wave. So, if this was, well, if you plotted out the value of sine as you increase, you get something like this, and this would be like a single note for us that we would hear. And that is, there's the two things in here. We talked about the volume. So the volume is the amplitude of the wave. So if this gets larger, it gets louder. If it gets smaller, it gets quieter. So this would be louder, and this would be quieter. And the other thing we have is the frequency. This would be a deep low pitch, and this would be a really high pitch. So it's basically the compression of the wave determines the pitch. So this would be deeper, and if we just look at where a full waveform, so when it goes from 0 to its maximum to its minimum and then back, so maximum, minimum and back, that's one wavelength there, and that's one wavelength there, so this would be higher pitched. All right. So when we're talking about computers, this is a very analog signal. So when I talk about analog, I'm talking about basically an infinite number of values. I mean, practically it's not infinite, but for what it's worth, you know, I can't tell if I'm making a noise with my vocal cords. I can't say, well, let's decrease it 1/1000th of a, you know, piece of tension or whatever. So as far as I'm concerned, you know, within the vocal register of what I can do from low to high, quiet to loud, it feels like there's infinite. I could make it infinitely more quiet a little bit at a time. And you wouldn't notice like the stepping effect of it's getting quieter by a fixed amount. It just sort of goes in this nice smooth curve down. Realistically, in computers, we don't deal with infinite numbers because computers effectively boil down to binary. Everything is a 0 or 1. So what we could say in let's say we have a waveform here that we want to try and recreate. So we want to recreate that in a computer which has two values, a 0 and a 1. We could say, okay, let's represent this by 1, let's represent this by a 0, and we end up with a waveform which looks like that. And if you play that, it will sound awful. It'll be very abrasive because it doesn't have any nice harmonics or anything. It'll be like a very mechanical buzzing sort of sound. And we'll see some of these different in 2 slides time, I think. They're called oscillators. They're basically things which generate noise, and you can generate them in different shapes. So, okay, 1 and 0. If we look at it, we've got all this area under the graph, or around the graph, which is actually not a very good approximation. We want to try and get this looking as much like this curve as possible because that will give us the closest reproduction of sound, sort of sound most like what we want it to sound like. So what we can do is instead of having 0 and 1, we can say, okay, well, let's do 2 digits. We have 0, 0, 0, 1, 1, 0, and 1, 1. So in binary, you can see this is just counting up. This is 0, 1, 10, 11, or if we were to write these out in their decimal equivalents, 0, 1, 2, and 3. And then what we can do is if we have our waveform like this, we could say, okay, well, let's make this 1, 1. Let's make this 1, 0. Try and put these sort of even. This can be 0, 1, and that can be 0, 0. And so then I might say, okay, well, let's sort of average this out for about that, it's there. For about that, it's there. That, it's there. That, it's there. Oh, that's not very even, is it? And what we'd find is if I had done a better job at drawing this, the areas we've actually got under the graph, or like which sit outside of the graph, will be slightly less than they were in the previous example. And so this would sound slightly better to us. And we can keep doing this. We could say, okay, well, let's add in a third one. Zero, 1, 0, 0, 1, 1, 1, 0, 0. And if we did this again and redrew it, we'd get slightly more accurate and slightly more accurate and slightly more accurate. But that's effectively what's happening when we do audio on a computer. We are trying to represent some waveform by basically breaking it down into these little steps. And we'll see some examples of that later on. But the reason that's important is because when we're basically trying to push sound out of our sound card, what we're effectively doing is that each, if we have some sampling time t, so if this is, say, 1 millisecond, and this is 2 milliseconds, and this is 3 milliseconds, what we're basically going to do is try and sample this as best we can, and then figure out the closest number to it, and then push that number out into the sound card, and that will move our speaker the appropriate amount. So yeah, sound is a wave of pressure. It has the pitch, which is the frequency, so how long or short those waveforms are, and we have the volume, which is the how high and low those the waves are. And we can basically approximate having a nice clean sound wave with or an analog sound wave with a digital form by breaking it down into these numerical waves using what's known as discrete sampling. So we're basically trying to split it up and put it into some boxes which our computers can work with. Okay, so there's why would we, well, probably don't really need to cover this so much, but some uses, I guess, for sound as a feedback thing. So you can have an audio icon, so you get a text message, your phone makes a noise, you know, oh, that's a text message. So it's basically gets associated with something in the same way that, you know, a visual icon would. A little notification pops up on your computer, you've got a new email, your phone makes a dinging noise. Either of that you know immediately without having to actually give it any focus or any attention, this has happened. Aid simulation, so this is something that Rob's really interested in. You guys had the research rodeo the other day, so everyone talked about all that stuff. So Rob's interested in things beyond the visual side of virtual reality. So, you know, sound is sort of the, I'm not sure the exact numbers, but visual processing in our brain takes up by far and away the largest amount of processing based on energy usage of all our senses. I can't remember the next one, whether it's touch or sound, but it's very important to us. Like, you know, if you ask a lot of people what if you had to lose a sense, most people would say they would like to lose sight the least because we rely on it the most, but sound is usually number 2 for most people. Most people feel like they could probably get away with losing your sense of smell or taste or touch, but, you know, sound is really important for making things feel realistic. And as far as simulation goes, that's quite important for the sort of stuff we do here at the lab. So if you think about when you're dealing with digital experiences, I have having been on this earth for a few decades now, I have a certain understanding, expectation about the environment. I know, as I'm sure all of you do, roughly what this is going to sound like when I bang it on the table. You know, before I did that, it's probably fine. And that's because of our experience with, you know, this is probably wooden table and stuff like that. But you can really change the realism of something by just affecting the sound. Like you can imagine if I dinged this on here and instead of sound like that, it sounded like that. Your thoughts, or actually even better, something like that. Your thoughts would immediately be, okay, that table's not actually made out of wood, it's made out of metal. That's surprising. So these sort of little cues can actually be quite different, quite important as far as making a situation quite realistic. If I look around, everything looks perfect, but when I interact with it some way, it makes a sound that I wouldn't expect. It immediately changes our mental model of, okay, this table looks like it's metal, wood, but it sounds like it's metal. Why is that? Is that a mistake in my perception, or is that something that I have, you know, our simulation is not actively reflecting? Likewise, there's all sorts of things, you know, if you think about low quality TV shows and movies and stuff like that with audio recording, you have a bunch of characters in a room and they've obviously overdubbed it. And, you know, in this room is quite a good example. It's quite small, we've got quite reflective walls. I can actually hear a little bit of reverb of my own voice bouncing off the walls, but if I'd have recorded this in a soundproof sound studio, it would sound very different. And you often get that, like when you're watching dubbed things, that it doesn't feel right because I've obviously recorded it in a different environment. So when we're trying to do simulation, you know, sound can vary. Even if you've got the most beautiful simulation in the world, if the sounds don't respond in the same way that the visuals do, or don't provide the same experience as the visuals, it can be quite jarring to the user and really throw them off that experience. Which I guess gets me on to the next point, telling information about the objects making the sounds. So the example of if I have something and I can bang it, even if I'm not allowed to touch it, like you could be on one side of the room, I could be on the other side of the room, or even if I'm blindfolded, you know, you could drop something and I could have a guess. It sounds like you've dropped something, probably plastic on something metal. But with that visual aspect as well, it really can help clarify our experiences and our expectations of things. Okay, yep, even without having the opportunity and the ability to interact with something, I can tell what it is simply by how the noise it makes and that sort of stuff. As an emotional trigger is something that horror movies in particular have done. They've really nailed this. So you watch a horror movie, more often than not, the things which make you jump is the noise of the, the harsh violin screech and stuff like that. It's not actually so much what you're seeing on the screen, it's that audio thing where there's a very, your audio perception runs through a very deep like part of your brain, like a very primitive part of your brain, which can actually trigger emotions before you're even consciously aware of what's going on. And that's, a survival technique. If you hear something, like you're in the forests and you hear the cracking of a twig, you might immediately think, okay, there's something else out here with me. I need to run because I'm about to get eaten by a tiger or something. Yeah, and so that's very important as well. Like, we've got all these different sort of ways of playing with sounds to trigger certain emotions in people. And if you're looking at how digital storytelling and stuff like that, you can use sound really to your advantage to try and invoke certain feelings in people. You can scare them by having, certain noises, or you can make them feel quite melancholic and nostalgic by having certain, particularly music which is played in flat keys and stuff like that tend to bring out this melancholic sort of sad feelings, and the major keys tend to be more upbeat and happy and can trigger that sort of stuff. And even what I was saying before, a little bit of an aside, there's actually a really interesting theory behind things like ghost sightings and stuff, in that they've found, not in all cases, although they haven't probably studied them enough, but they've found in certain cases that places which are particularly haunted actually have certain acoustic properties, which means they have very low frequency audio, which is actually almost imperceptible to what we are able to hear. But the hairs in your ears and even the hairs on your arms and everything are able to detect this thing, and they bring out certain primal instincts in us. So there's one, for example, that I was reading about. It was in this place in the States, like an apartment building or something, and it had one of those big ventilation fans on the roof. But the fan was moving at a certain frequency, which is actually very similar to the low frequencies in a lion's roar. And so for people who are particularly in the basement of the building, because of the acoustics, they often perceive this feeling of dread and constant fear, and they get in there like, oh, this place is haunted. But really what was happening was this fan was actually stirring something deeply primal in people's senses. It was as the same sort of things of a large predator has in their roars and their behavior, that people, it would kick off this experience that something bad is about to happen, and people would then start attributing it to, oh, this place is haunted. And there's other things as well. They've detected certain frequencies can actually play havoc with the fluid in your eyes and cause you to start seeing dark shadows at the edge of your vision, because it's causing the fluid in your eyes to start pressing on your retina. But kind of a bit irrelevant to what we're talking about here, but using sound as an emotional trigger is actually something which can be very potent, and I think probably in gaming and stuff like that is something that has become more prevalent recently, as people become sort of more aware of all these things we can use to affect people. And it can also be used as a product of play. Where's the remote before this blares out incredibly loudly? I left it over there. Just because I have no idea what the volume on the TV is. Well, actually I do, because it was just dinging. So this is using sound as, rather than, I guess, an enhancement, as the core element of an experience. So this was something, I'm not sure if this one was done in processing. Yes, there is audio. But there have been similar things done in processing as to this. Does it say? Blah, 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 blah. Oh, okay, not so much, but that's okay. So the idea behind this is they're using some computer vision tracking algorithms with a cool little, so they've got a camera and a projector mounted above the table. They're using some computer vision to detect these blocks on the table, and each block has a certain aspect. So we can see things in here, like this square one here is basically outputting a square wave, which is like this sort of thing here, where we have boxes rather than curves. And you can see they've got a bunch of other shapes, so a nice sine wave in there. They've got, what else have we got? A saw wave and some other bits and pieces. Some of them are just used for playing audio. But the cool thing about this is they've got all these interesting interactions between these various blocks. such that when you move them together, you can chain them together and create like your own sort of synthesizer stuff. And you can rotate them to change the frequency and the volume and all that sort of stuff. So just sort of showing the interaction between them. So this is changing, you can see there they're changing the wavelength. So the wavelength gets shorter, the pitch gets higher. Before they were turning that thing, it was increasing and shrinking the size of the wave, which increases and shrinks the volume. So we fast forward because this is a long video, but it's worth it. So by chaining together very simple audio effects, you can actually make some quite interesting sort of experiences. And the whole thing about this is basically an audio experience. Everything else here is just to allow people to more easily interact with audio elements. So you get some pretty cool stuff there. Just chaining some very simple sort of effects together. If you know what you're doing, I would argue that this is getting more of art than science. And I just say that because I'm not particularly artistic and it's something that I can do. So, but it's pretty cool. So there's arguments as well for having audio as just the sort of main motivator. We had a master's student here, I think one of our first master's students actually, who was from the School of Theatre and Performing Arts, and he was really into poi and all that sort of stuff, and put together a thing using a PlayStation Eye camera, which basically would track poi, and depending on how you spun it, would start generating music. So he was doing stuff like this, and basically depending on the speed you spun it would depend on the playback speed of certain things. You spin it faster and faster, and the music plays faster and faster, or you spin it larger, increases the volume. He then ended up throwing some training stuff in there as well. So you'd see a projector of yourself, like the camera in front of you, a projector behind you shining on a screen, and there'd be like various things on the wall that you had to spin the poi through. And it was quite a cool wee demo. He's now, I think he's working at Lincoln or Otago or something, but he still goes around. He's a festival guy, so he goes around all these festivals. He's managed to shrink his entire system down to fit into a little briefcase sort of thing now. So he goes to festivals and he pops it open and starts the software on the laptop, and he's got the projector and camera. It's quite cool. It's really interesting sort of example. Okay, so as far as sound and processing, there's a few different ways, or a few different things in there which allow us to do quite a lot of stuff. So there is the processing reference manual for sound, which is the sound library for processing. So this morning I thought I better check this out. So sound used to come installed by default in processing. It, for some reason, doesn't anymore. So you have to go into Add Library, search sound, and you'll see in there sound provided by the Processing Foundation provides a simple way to work with audio. And so you can just install that and have the sound working. Now, a bit of a caveat here, I suppose. I've found in previous MHIT courses, certain people's computers just will not run the sound library, and I don't know why. We have done assignments before where they built their own MP3 player, and some people just could not get it working on their laptop. So we're not going to be building an MP3 player for that reason this time round, but you're welcome to have a play with it. As far as I've been able to tell, in Unity all their sound stuff works regardless of computers. I think it's just a weird Java thing, so be warned that if it doesn't work, use a different computer. So you'll notice after we've done that, we can go import library, and it will appear in the top set, which is a little bit counterintuitive because all the other ones we install appear in contributed, but sound appears in that one. And likewise, when we were looking at processing the other day, clicking on import library will bring in import processing sound, and then we can start, doing some stuff with the sound. So there's three main sort of classes. three main things. There's audio device, which allows us to do some stuff with the hardware access, so we can choose what sound device we want to use, whether it be a microphone or a speaker or whatever. And then there's the two main parts of audio is obviously output and input. We're either playing some or making some noise or listening to some noise. So an output, the one that people most commonly use is SoundFile, which basically allows you to load a file. I think it supports, if we go back to here, I think it supports WAV, AIF, and MP3. So, you know, you've got a few different formats there which work. And then we've got a bunch of various generators. So these are things which allow you to create noise based on mathematical formula and equations. So you have oscillators which can produce sine waves and square waves and saw waves and triangle waves and all that sort of stuff. You can have noise generators which basically just create waves which are just random, and so they make noise. So you're probably familiar with things like white noise, which is that sort of TV static. If you turn on your TV and you're not tuned to a channel, that's white noise. But there are other noise. There's pink noise and brown noise and grey noise and stuff. And then for input, we have the audio in class, which provides a bunch of high-level methods to record sound. I'm not sure why player's in there. Yeah, so audio in provides a bunch of examples to record sound. So we're going to have a look at some examples. So starting with audio output. So you'll notice in some of these slides I have down the bottom here what kind of look like paths, and they point to examples. So once you've imported the sound library, and I actually had to restart processing to get this to pop up, if you go to examples and then close some of these up, you'll notice that we have libraries and then sound, and if I open that, we'll see there is a sound file, and then in that folder, finally, there is simple playback. And if we open that, this is basically what some of these ones are looking at. So let's close that and slide this over here. So if we want to play a file, all we have to do is say sound file. So sound file is a particular class. So we're going to create a new sound file object from that class. Awesome. Undo is not working for some reason. I have a feeling the keyboard on my laptop's past its best by. So we create a new object of class sound file, and we basically say new, so call its constructor. Again, we have this thing that we saw in Control P5, so we're passing an instance to our program to allow sound file to do any callbacks that it needs to. So hook itself up to the draw method, for example, so that it can update the sound. And then we have the name of the file. So in this one here, we have, you'll see that more or less that exact line of code. I've declared sound file up here so they can access it the whole program, but down here we have sound file equals new sound file, this vibraphone.aiff. So if we go into Sketch, show Sketch folder, you'll see in the data subfolder that there is this vibraphone.aiff. And if I open this in something that can play it. So this is basically the AIFF file, so it's like a compressed audio format, and this is what it sounds like. So what this program is going to do is it's going to load this sound file, and then it's going to tell it to play it in a loop. So there are two options. There is play and there is loop. Play will play the song from the start, or the sound file from the start to the end. When it finishes, it will stop. Loop will play it from the start to the end, and when it finishes, it'll start back at the start, and it'll keep going until you explicitly tell it to stop. So if we run this code, turn that up, so you can hear that sound file playing. So there's a few other things which are going on in here. So we load the sound file, we tell it to play in a loop. In the draw method, there's a few additional things which are going on. Let me just silence that for a second. So you can see we're doing three things to the sound file. We're calling .rate on it, we're calling .amp on it, and we're calling .pan on it. So these three things, rate changes the speed of the playback. So as 1 is play it back at normal speed, if we play it back at 0.5, it will play back at half speed. If we play it at 2, it will play at twice speed. We have amplitude, which is the volume. So as 1 will be max volume or normal volume. If we go 0.5, it'll be half volume. If we go 2, it's twice volume. And panning is which speaker it's coming out of. And it's, unless you go and stick your head up against the screen, you probably won't notice it. But if you do these examples wearing headphones, you notice as you pan, you can hear it move from one side of your head to the other. So panning is good when you're sitting directly in front of the thing, or you have some sort of surround sound, or you're wearing headphones. Probably not going to be too noticeable here. So what we call these rate, amp, and pan functions with, you'll notice we have these playback speed, amplitude, and panning. And there is a function here called map. So map is actually quite a useful function, probably one of the more useful ones I've come across in processing, and no other language has it by default, which is a bit of a shame, or no other language that I use with any regularity. But what the map function does is it has 5 variables. So it has in, which is a value you pass in, and then it has in max and out max, which is the minimum and the maximum that value is likely to be. It can go inside or outside of those, but this is basically where we're going to assume it to be. And out min and out max will be the value that gets returned by this function, and it's basically going to map this value in between this range to this range. So for an example, if I had something like map 0.5, 0 to 1. So basically I'm saying the in value is 0.5 and the min and the max are 0 and 1. So in this case 0.5 is halfway between them. Let's map that between 0 and 100. So what that's going to do is it's going to say, okay, where does this fall between these two numbers? Well, it's at halfway. So in this case, the returning value should be halfway between these two values. So in this particular example, it would be 50. Or if this was something like 0.25, this would be 25. And these numbers can be anything. So I could say, let's do this between 10 and 20. And now this will be, if this is a quarter of the way between these two things, it'll be a quarter way between these two things, which will be 12.5 from memory. So it's just a really nice sort of helpful function to map a number between one range to a number between another range. So we can see in these examples here, what they're doing is for the playback speed, they're mapping the mouse X position, remembering that if we have our screen like this, mouse X will be our position somewhere along the horizontal axis between 0 and the width of the screen to 0.25 and 4. So basically what we're saying is that this will map to 0.25 and that will map to 4. So if our mouse is at the far left of the screen, playback speed will be 0.25. If it's at the far right of the screen, it'll be 4. If it's in the middle, it'll be halfway between those two numbers, which is something that I can't figure out off the top of my head. But basically it's allowing us to map the left-hand side of the screen 0.25. The right side of the screen is 4, and the middle will be, well, everything between that will be the same fraction. So if we run this example again, and I turn this up so it's loud enough for us to hear. So if it's very low, very far left, you can hear it's playing really, really slowly. So that's playing at 1/4 speed. So that's, I don't know, around 1-ish. And then as we go more and more to the right, it's playing faster and faster until we get to the far right of the screen. Now it's playing 4 times the original speed of the file. And you can hear it just finished then, and now it's restarted again. So we have the same thing for amplitude. Amplitude maps the mouse's Y position from 0 to height, and it's going to, oh, sorry, 0, okay. Amplitude is mapping the mouse Y position between 0 and width, which doesn't actually make any sense. So let's change that between 0 and height. And it is changing, it's going to map that so when the mouse Y is at 0, so at the top of the screen, it's going to be 0.2, or so 20% the volume. And if it's at the bottom of the screen, it's going to be 1, which is maximum volume. So hopefully, no, other way around, sorry. So when it's at the bottom of the screen, it's going to be at 0.2, so barely audible. And then as I move up to the top of the screen, it's going to go up to the maximum value of 1. Why that was width originally, I don't know. I suspect that was probably a mistake in the example, so feel free to just assume that's height. Likewise, they have the panning, which is actually possibly why that sounded a little bit weird. I'll just comment that out. Yeah, so that's how it should have worked. So it's at 20% of its volume at the top, and then as we move it down, it gets louder and louder. What I think we'll find is that the panning, which is whether it comes out of the left speaker or the right speaker, so only one of the speakers is working on this TV, which is why it's getting quieter, or possibly through the sound capture or whatever. So we can hear it. We can hear it quite loudly when it's coming through, when it's set at -1, which is probably the left speaker. When we try and move that down to the right speaker, it's going quiet. So I suspect something between here and the TV is only sending through the left audio channel. Okay, so playing a sound file. Create a new sound file with the name of the file you want to load. Call play to play it. Call loop to loop it. There are a bunch of other functions you can use on sound file as well. You can jump to a specific position. You can pause it. You can figure out how long the duration is. You can stop it. We can tell whether it is playing or not. So there's a bunch of other functions in there that we might want to play around with. And we can control its speed with rate. We can control its amplitude with its volume with amplitude, and we can use pan to move from left to right. So that's the main way of generating audio. It's usually much easier to create the audio beforehand, so record something with a microphone or whatever, and then play it back. But if you do want to create audio from scratch, you can use, like we saw in that example, you can use things like oscillators and generators. So if we open the oscillators subfolder, so libraries, sound, oscillators, you'll see there's a bunch of different sound files in here. So if I open sine wave and we have a look at this, so you'll see most of these oscillators have some name OSC, the oscillator. So in this case it's a sine wave or a sine oscillator. So we've set that to a new sine oscillator, again passing in this, and we just call play. We don't need to call a loop on oscillators because they effectively are just one wave anyway. So if we played it, it would be over almost instantaneously. So we call play, and that will keep playing it. This one has the same sort of thing. We can pan left, pan right, or move the mouse left to right to change the frequency, move the mouse top to bottom. So you'll notice it is actually height this time, not width. And let's pull out panning because this TV doesn't work right. But we can play a sound away. This is a sine wave. So as we move left to right, it's changing the frequency. So it's changing it from, as we move left to right, something which looks like that, to something which looks like that, to finally something which looks like that. And that ends up changing the frequency that we hear. So it starts very low pitch, and then it will get higher and higher and higher pitch, and volume from bottom, from quiet to loud. So that's a sine wave. There are a bunch of other waves in there we might like. So square wave is the other one we've looked at, which is just when we draw squares effectively rather than that. And you'll hear it's a much more abrasive metallic sound. It's not a sort of smooth and is quite, kind of very 1980s like video gamey sort of sound effects because when you're talking about like these 1980s games which didn't have a lot of memory, you didn't want to have to assign, a ton of memory to do a simple sound. It's much easier to say push a 1 out and then a 0 out, so they could play often use these things to save on memory. There are a bunch of other ones. So a triangle wave is, as you would expect, a triangle. Is slightly warmer sounding, I guess, than a square wave. It doesn't have it still has sharp edges, but at least they're sort of on a line rather than straight up and down. So not quite as kind of awful sounding as the square wave. We've got a saw wave, which actually let me just. So this is the saw wave here. So it looks like, whoops, a triangle. Was that one there? Yeah, here we go. So a triangle wave looks kind of like one of those, but if you drew it with sharp lines. A saw wave is more like teeth on a saw. So it goes up and then it has the abrupt drop down. So if you think about it, this is quite a smooth sort of sound. That is smooth-ish sort of sound. This is a very abrasive sort of sound, and likewise, that is a very abrasive sort of sound. So it's more to do with how we chain, like the transitions in the waveform depending on how it sounds. So this is quite smooth, this is quite smooth. Because we have this, immediately going from a 1 to a 0, it's quite an abrupt sound. Same thing here. Whereas this is sort of going from a 1 to a 0 on a smoother angle, likewise, that one there. So saw waves and square waves are less pleasant to listen to than the other two. Where's processing going? Yeah, so we have saw wave, sine wave, square wave, and triangle wave. We also have pulses that we can push out. So a pulse wave oscillator. I'm not 100% sure actually what that looks like because it's not a common one. Do we have it looks like possibly like a square wave again. I'm not sure, but again, it wouldn't be surprising because that's not a particularly pleasant sort of sound. So we can generate all those sounds and we can add them together as well. So when we're talking about, if we were to draw out sort of, obviously these are all like one frequency, so they just are one noise. If we were to play back how my voice sounds, for example, we'd probably find that it looks something like this as I'm talking, and that can actually be broken down as adding a whole bunch of various waves together. So you might say, okay, we can approximate this by having an initial sine wave, and then maybe we'll put a more high frequency sound wave into something, and that will, if we add those two sine waves together, we're going to get something which sort of goes like this. And so we can start having all these various waveforms that we add together to, again, try and approximate this shape. And that's exactly how things like audio compression work. So if you compress something to an MP3, what it's trying to do is find a bunch of, rather than representing each of these as numbers, so if we say this is 0 and this is 1 and this is -1, or rather, should I say that's 1 and that's 0, rather than like we did before and we said, okay, well, if we do that, we end up with quite a sharp wave, so let's make that 0, 0 and that 1, 1. Oh, that's still not close enough, 0, 0, 1, 1, 1. And keep on adding more and more bits to it. We could basically just say at time t, let's make that time 1, the value is equal to 1000110, and then at time 1.1 it's 100101 sort of thing. We can record each of those values at each point in time and play them back, and that will give us a perfect rendition of the sound. And that's basically when you have a wave file, that's basically what's kind of being stored in there, the value at each point in time. When we try and compress that down, what we're trying to do is find a bunch of wave files, or sorry, a bunch of like waveforms that we can try to approximate what this looks like. So there's a bunch of things, what's it called? I think the Taylor series. Which will basically add, something like this. So we have if we have a 100 hertz frequency wave and a much smaller 50 hertz frequency wave, when we add those two waves together, we end up with something like this. And you can imagine if we kept on adding more and more waves together, we'd end up with, we could sort of recreate any of these shapes as long as we sort of said, okay, add this this wave for, 0.2 seconds here, add this wave, or add this wave from 0 to 0.2 seconds, add this wave at 0.4 seconds, whatever. We can actually start to approximate these waves. So theoretically, you could do the same thing with this. You could start adding various waveforms together and to try and create different sounds if you want. So I think this is, so this is sort of doing, this example sort of does that. It takes a bunch of sine waves and tries to add them all together to end up with something more than just a single frequency. How do we control this? Frequency detune. So, I mean, still not quite as obvious, but if you listen, you can sort of pick out there's at least two frequencies in there. There's a higher pitch one and then there's one a bit lower. As we move from what it looks like in here, as we move the mouse from left to right, it will try and bring them back into tune. So you can hear about there, they're about the same sort of frequency, but as I move you can hear one sort of stays where it is and one gets higher and higher frequency as we go. So there's always that sort of background hum, and there's one which is moving, although apparently there's actually 5 sound waves in here, and that's just changing the frequency of all of them. So yeah, you can add them together. Obviously that is quite difficult unless you're like that person who was playing with the reactables thing before, so I wouldn't recommend that. It's probably much easier to record your sound. But there are other things in there. So we talked about noise generators before. So processing has some noise generators. So there's a white noise generator. Again, the class is called white noise. Create the object, white noise this, and we can change the pan and the amplitude. So white noise, brown noise, and that, they're all generated with different sort of like random number generators, effectively, and they all sound slightly different. So this is white noise that is probably most familiar to most people. So TV static. There are other ones. So brown noise is a little bit more bass from memory. So like waves crashing on the beach. And I think pink noise is kind of between the two of those. Can't really hear it very well, but not quite as harsh and abrasive as white noise, but not as bassy as brown noise as well. So there are various things you can do to generate, audio thing, but realistically, most people are just going to play back a sound file because that's the easiest way to deal with it. Let's actually do audio input and then we'll have a break because at least that way we can finish a topic. So putting audio out is one thing. We can also support audio input. Again, this is something that I have noticed tends to work better or worse on certain people's computers, so it may not work for you. But under Library Sound I/O Audio Input, there is a nice example which does that. So we have audio in, which is audio in class and input. So we're going to create a new an input thing, a new input object of audio in. This again, and this 0 here is basically saying what device it should be using. So you can usually leave this as 0. If it doesn't seem to be working, try changing that value in there. Most laptops will have one microphone in it, which is usually with the web camera. But if you plug a different microphone in, or if you plug a web camera in, a different web camera or whatever, and something with its own microphone, you might need to change that number to get the audio from the different device. And then we just call input.start, which will start the audio capture. So the other thing in this one, so calling audio input will start recording audio, and you can get that audio. Where are we? You can get that audio out of the audio input. Can we? No, we can't actually. I tell a lie. So what you have to do is you have to have an audio analyzer like Amplitude, which will get you the basically takes the audio input and does some processing on it. I thought there was a way to do, yeah. So there are two ways of doing audio input or there's two ways of processing the audio input. You can do the amplitude, which will just tell you how loud something is, and then there's FFT, which stands for Fast Fourier Transform, which will break down the audio into bands and allow you to analyze that. I thought there was a way to get the raw audio, but I know there is in Unity, but apparently not in processing. But anyway, so we create a new audio input object, we tell it to start, and then we create a new, you see here we have this amplitude class and we have this loudness variable. So we're going to create a new loudness object or amplitude object and assign it to loudness, again passing in this. And then we use loudness.input to say that, so input is an analyzer, or amplitude is an analyzer, sorry. We say use the input from that, should be coming from this audio in. So we have input, the input variable is an audio in object, and we pass that into loudness. So that loudness will now start getting data from the audio in and processing it. So in our draw method, all we're doing is, again, we're mapping the input level, so that's just going to change the amplitude in that. So as we move the mouse from top to bottom, it'll change how loud that processes it. And then we called loudness.analyze, and that will return the volume at the current point in time. And then we calculate the size by mapping that, and we draw an ellipse. So let's run this and hopefully it will work. So yeah, you can see here there is a little pink circle, and that pink circle is being drawn based on the loudness. So this loudness analyzer is taking in all the audio, and it's basically outputting one value, which is just the current, or how loud the current thing is, what the current amplitude is. So I can change this, I can move my mouse from top to bottom, and that will change. There's this loudness.amp, which is the amplification. So as I move down towards the bottom, it's going to amplify it more. So theoretically, if I move this towards the top, it doesn't actually seem to be making that much of a difference, but should be slightly smaller circles at the bottom compared to the top. Yeah, and so that's basically showing what the microphone is picking up. So as I talk louder or click my fingers, you can see the circuit gets louder. If it's quiet, circuit was very small. So that's a very simple example, and you can think of it as like a one-dimensional sort of thing. If you want to create some game or something where it depends on how loud the person's talking, or you have to clap your hands or something, you could simply measure the loudness, and if the volume is over some threshold, you can say, okay, that is likely to be, whatever we're looking for. So the other thing, I'll throw this in here as well actually, is Fast Fourier Transform. So fast Fourier transform is basically tries to, from a waveform that comes in, tries to break out the various, so we looked at this example here where we could make up a sound wave by various waves. What a fast Fourier transform does is it tries to do the opposite of that. So it tries to figure out the sort of wavelengths that would be required in order to make an audio sample. And because the wavelengths that we add together tend to be, we'll add this waveform and this waveform together, we know that the difference between these two waveforms is this one, because it has a much longer wavelength, is going to be much bassier or have a much lower pitch than this one. What the fast Fourier transform allows us to do is effectively allows us to break out these various waveforms based on their pitch and the relative volumes. So if we run this example here, so this one's just playing an audio file back, but we can see this visualization here is being generated by the fast Fourier transform. And so down the bottom here we have the lower wavelength, so it's calculated that there are some lower wavelength waves which go into making up what's being played out here. And so that's left to right is the pitch of the waveforms, and top to bottom is their amplitude for how loud they are. So this is quite a bassy sort of song. So you'll notice that there tends to be a lot of representation in the bass. There's not a huge amount in the higher pitches, there's not so much there. So theoretically we could, let's give it a try. Let's change this. So this is taking a sound file. There's a bunch of stuff in here which is set up to do rendering, but it's taking a sound file and it's looping it, and then it's creating a new fast Fourier transform, and it's using that sound file as its input sample. So let's take our example before, which did audio input. Instead, I have no idea whether this is going to work, but we're going to find out very shortly. So we're going to, instead of having a sound file as our sample, we're going to have an audio input, or audio in, sorry. We're going to comment out everything which loads and starts playing the sample, and instead we're going to start our audio input, and we're going to pass that input into the fast Fourier transform. And hopefully, if this works, we now have a waveform which is basically showing my voice. So you can see there's still majority, at least in this fast Fourier transform, the majority of my voice tends to be bassier. That's not because I'm Barry White and have a super deep voice, that's just there is a limit of vocal range that humans can make. So, if we had an opera singer here singing at high pitches, we'd expect to see a lot more in the higher range. If we did have Barry White, we'd probably see less of, you can see this sort of tailoring down. His voice would probably be much lower in the spectrum. And it isn't like this value here is 0 either. This will continue on bassier and bassier. It's just in this particular example, they chose this as the cutoff as being the leftmost point. So if you want to have a try at this, try and sing your highest note or whatever and see how high up the scale you can get. We can have a little contest if people want, see who's M-Hit's next great opera singer. But otherwise, let's have a break there, and we'll come back in about 5 minutes or so.